Welcome back. This is our last so-called online class. On Thursday, we're going to run a review on the Zoom, and you will have your last quiz to do on Thursday as well. So, to remind you of the end of semester details, your last classwork is due Wednesday, December 8th at 10. The optional homework is due Thursday, December 16th at 10 a.m., and the final exam is on Thursday, December 16th. It is on the Respondus, and it runs from 9 a.m. to 10 p.m. It is timed for 3 hours and has about 35 questions, and it covers the entire semester. Alright, so next we want to look at the physics of an atom. The first big discovery in this direction was the Balmer lines. So, Balmer analyzed the hydrogen lines, which were found when hydrogen gas flowed past a spark. Light was then shined through the resulting plasma, and it was found that there were certain bright lines at specific wavelengths of light that was produced by this mixture. From this, it suggested that hydrogen produced a very precise wavelength of light when it was exposed to a spark. This result was then analyzed by Balmer, and he found a pattern in the hydrogen lines. What he found was that the inverse of the wavelength of light corresponded to a difference between two values, both of which are a number divided by an integer squared. So he found that all combinations of this pattern could have lines in the visible spectrum had lines in the visible spectrum. So based on what we know now, this is because the hydrogen atom has energy levels that it can belong to. Instead of having all possible energies, like a classical object, the hydrogen atom can only have electronic energies that correspond to minus 13.6 eV divided by an integer squared. So if n is equal to 1, then negative 13.6 divided by 1 squared is negative 13.6 eV. If the n quantum number is 2, then the energy is minus 13.6 eV divided by 4, because 4 is 2 squared, and that gives an energy of minus 3.4 electron volts. So the first transition would be from n is equal to 1 to n is equal to 2, and that is 10.2 electron volts. But the result that really breaks from classical physics is that atoms have electronic energies that can only have specific values. It's not a continuum, there's only specific values. Okay, so to solve this sort of question, we do it like this. What is the energy magnitude for a transition from n is equal to 3 to n is equal to 1? Well, we can use our formula here, 13.6 eV times parentheses 1 over n final squared plus 1 over n initial squared. If we do that, we get 13.6 times 1 over 9 minus 1, which gives us negative 8.9 times 13.6 eV, which is minus 12.09 electron volts. The minus is because energy is released in this process. The atom de-excites from an excited state to the ground state, so it will emit a photon with this 12.09 electron volts. If the energy were positive, then it would be an excitation. The atom absorbs a photon with the 12.09 eV of energy. So this question asks for the magnitude, so technically our answer here is just 12.09 eV. So, that is the empirical experimental side of this discussion of the atom, but on the theoretical side, they were dealing with a problem as well. So this is later after Rutherford and his co-workers discovered the nucleus. So the new model for the atom was a negatively charged electron orbiting an ultra-small, positively charged nucleus. The problem here is, why don't electrons just crash into the nucleus? The Earth's orbit is stable, but that's because things with similar masses aren't crashing into the Earth all the time. But with electrons, why don't they just crash into the nucleus? So Niels Bohr proposed a new model for the atom, which at least partially solved this problem. So Bohr assumed that the electron orbit of the nucleus is a circular orbit, and that this could be done at certain radii without emitting electromagnetic radiation. He also assumed that the angular momentum of the electron was quantized, that is, it could only have precise integer values times a constant. Then last, he assumed that the atom could absorb or emit radiation when transition between these levels occurred. This allowed us to find the velocity, radius, and angular momentum of the hydrogen atom. Once we know this velocity and radius, now we can find the energy of the hydrogen atom. And it turns out that this leads to exactly the formula for the hydrogen energy levels that had been worked out qualitatively before. And this formula works for any one electron atom. So helium plus 1, lithium plus 2, and so on. In this formula, Z is the atomic number of the atom, so this becomes Z squared divided by N squared times the 13.6 electron volts, and that gives you the energy of any one electron atom. If we have more than one electron, then there are electron repulsions or correlations that change the energy, and this makes the energies much more difficult to calculate. So the Bohr model breaks down for multiple electron atoms. But it gives a quantitative explanation of the hydrogen atom, and it is a very clear improvement over the existing models. And this leads to an accurate model for one electron atoms. So if we want to find the energy of any one electron atom, we can use Bohr's formula. This works just like the hydrogen atom formula we did before, but now we have this Z squared term, which is the atomic number of the atom. So let's do an example. Here we are doing the one electron beryllium atom. Beryllium has an atomic number of 4, so Z here is 4. So we are asked what is the highest energy transition for n is equal to 2 in the beryllium atom. So that is the transition between n is equal to 2 and n is equal to infinity. So notice, when n goes to infinity, it becomes 1 divided by infinity squared, so that value just goes to 0. So the energy is 4 squared times 1 over 2 squared times 13.6 eV, and this becomes 54.4 electron volts. So that's a lot of energy, and we can find the wavelength with our 1240 eV nanometers divided by 54.4 electron volts, and that gets us a wavelength of 22.8 nanometers. So this is UV, but getting pretty close to the X-ray energy range. This is why X-rays are used in imaging. They are absorbed by atoms with large atomic numbers, but not atoms with the smaller atomic numbers. Okay, so you have a few questions to answer, and then we'll finish off our unit on quantum physics in the next video.